Hello, this is Lecture 9B, Part 2, Lhopitals Rule. My name is Scott Grizzard from the University of South Florida. Just to remind you, there was a Part 1 to this lecture, but by a student's suggestion, I've split it up. Into two separate videos. Still the same lecture, but two separate videos. What we've got here is Lhopitals Rule. This is 3.7 in the book. Now, one thing that's interesting in the book is that the book presents Lhopitals Rule before the full version, before you actually have the machinery to do the proof of it. Okay, so what we're going to do is we're going to talk about it now briefly, and we've already talked about it before, and then we're going to come back to it. So we want this bigger version that was a little bit more than we had before, because we're going to use it for to do some of the stuff on concavity and the stuff on shapes. And then after we've done mean value theorem, we're going to come back to Lhopitals rule. We'll prove it in an extra. And then what we'll do is we'll play with it some more and more of its power. But I want to go ahead and introduce it so that we can use it to do some of these other problems. Okay, so recall that we've actually seen Lhopitals rule before. So if we go back to linearization, this is lecture 8a, we had this idea of the ratio of the linearizations, and that I could determine the limit of the ratio. And if both of those, the limits of both f and a and g of a were both zero, if I was heading to zero on both the top and the bottom, I could take the ratio of the linearizations, and these two things would go away, and all I would be left to is those two things, and those two things would cancel. The x minus a would cancel on the top and the bottom, and all I would be left with is the f prime of a over g prime of a. But I had this limitation that g prime of a couldn't equal zero. Okay. Well, it turns out we can lose that restrictions if we add. If we want to lose that restriction, we can. We have to add one more, but it's in one sense it gives us a lot more power to play with. So let's look at the full version of Lhopitals rule. Now, there's actually two versions of Lhopitals rule, the big versions, right? There's a 0 over 0 and an infinity over infinity. So let's look at the 0. It's actually two separate theorems. And that's important to remember. And I've got zeros over zeros, and then I've got infinite things over infinite things. And they could be negative infinities over positive infinities over negative infinities, negatives infinities over negative infinities, positive infinities over positive infinities. That shouldn't need to be said. But what we're going to do is we're going to look at the 0 over 0 version first. So I still got the same condition. This is the same as before. F prime of x and g prime of x both defined at a. You have to have that. But I had a little bit more restrictive. They have to be defined near a. And the reason for that is because I'm going to use the mean value theorem to prove it later on. And then I need g prime of x to not equal 0 near a. It's okay if g prime of a equals 0. But near a, around a, there has to be some little neighborhood around a where g prime of x is not 0. I can't be like constant or always going to 0 for this to work. Okay. And the mean value theorem is going to have, again, a big deal part of that. So this is the thing we're okay now with g prime of a. Oops. So we're okay. These are the two big things. We're okay if g prime of a equals 0. And it still needs to both be 0. So both the top and the bottom need to be going to 0. Then the limit as x goes to a is f of x over g of x equals the limit as x goes to a of f prime of x over g prime of x. Why do I care? I can do it more than once. Okay? Let's look at this. So here's something that I couldn't do with the baby version. The top here goes to 0, and look what happens to the bottom here. Sine of x squared. This goes to 0. But notice that when I take the derivative, I'm also going to wind up with something that's equal to 0. Okay? 2 sine, 2x cosine of x squared. Right? I'm going to wind up with something that goes to 0 because of the x that's going to be in front. And that's bad. So the original Lhopitals rule could not deal with this. But this one can. Show you what I mean. So what I'm going to do is I'm going to take the derivative of the top and the derivative of the bottom separately. So I've got 0 over 0 And it's very important that you actually indicate that. And then the name of the theorem, Lhopitals Rule, LH. Everyone just writes LH. Even the book writes LH. So this is not some crazy thing that Scott's doing. This is a normal thing. Now I'm going to take the derivative of the top and the ratio of the two derivatives. Well, the first one's easy. That's just going to be 3x squared. The bottom is going to have a chain. Okay, now when I sub in 0, again, I still have 0 over 0. And that's not good. I can't do anything with that. I can apply Lhopitals rule again. So let's go again. I've got 0 over 0, so let's go again. Ugh, I'm going to have a product rule on the bottom now. Okay. Now, this bottom bit has a chain, and I'm going to skip the whole U step. I'm just going to say, trust me on this. And then I'm going to mess it up, right? This part gives rise to a chain, so it's going to be 2x, right, is the derivative of the inside. And the outside is going to be a negative sine x squared. I've got a cosine of x squared. Ooh, and I've got a 2x. It's still hanging out. So one of those two x's was generated by the chain. The other one's just baggage. And then I've got a cosine of x squared times 2. Now, this is actually a happy thing for me, believe it or not, because this term right here is 0. That 4x squared becomes a 0. But this cosine of 0, that's 1. And then this is going to be 2. So this is no longer a 0 over 0. In fact, this is now a 0 over 2. And 0 over 2 simply equals 0. Okay. So that's the first problem here. I just did it twice. Let's look at another one. So here again, I'm going to wind up with a, if I sub in 0 here, I wind up with a 0. And here I'm going to wind up with a 0. So what I'm going to do is I'm going to apply Lhopitals rule. That u is sine of x, because this is really sine of x squared. And the 2's are going to cancel. Okay, so I'm left with sine of x times cosine of x. So I'm still left with 0 over 0. Let's go again. Well, that's actually kind of nice, because notice here, I've got a 1 on the bottom. It's going to go bye-bye, okay? So now all I've got left is the product. I mean, all I've got left is the top bit. Okay, and I could go, oh, that's cosine squared minus sine squared, and then do, like, convert it to the, I don't need to do that. Okay, so I've got, this is the derivative. These are supposed to be x's, not h's. So now all I need to do is I just sub in my 0. So 0 times a negative 0, this is a 1. And that's just going to equal 1. So I did it twice. I took the derivative twice, and I wound up with that. Okay, so Lhopitals rule, there's also an infinity over infinity version. And it's got the same. So it is the exact same theorem, except instead of this, I've got plus minus infinity as my two conditions. All the other conditions are exactly the same. Okay. So let's give an example. If I take the limit as x goes to infinity of e to the x, well, this goes off to infinity. This goes off to infinity. So I did a Lhopitals rule. I wound up with this. I did another Lhopitals rule. I wind up with e to the x over 6x. Let's go again. And now the bottom goes to 6, not infinity. So I have lots with e infinity over 6, and that's okay. And that just equals infinity. So those are the types of things I can do with the big boy version. The point is that I can repeat and repeat and repeat and repeat and repeat until I get something I can use. Okay? So again, we're going to come back to Lhopitals rule and do some other interesting things. Now, I assigned in the book, I assigned the example 6, which will deal with products. So look at the book and look at how to deal with products and try to figure that out for yourself. We're going to be coming back to this. Basically, you convert them into quotients. We're going to be coming back to this topic again, but we need it to do a couple of the problems. So we're just doing it now, and then we're going to do it again when we get mean value theorem and be able to prove stuff. Okay. Well, that's it. Don't forget that there's a part 1 to this lecture. Both should be together in your notes as one lecture. I'm just splitting them up because students suggested I had separate videos. And I will see you guys next time.